Hello, in this video we will understand Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction is the very basic concept and the most used concept in electrical engineering. So we will try to understand this law. Basically, Faraday's law of electromagnetic induction is a law which says how EMF is generated in a closed conducting loop whenever it sees a change in magnetic flux. So we can say Faraday's law of electromagnetic induction as whenever the magnetic flux through the area bounded by the closed conducting loop changes, an EMF is produced in the loop. The produced EMF is given as E equals to minus d phi by dt. Carefully observe this expression of EMF induced in the closed conducting loop. Here d phi by dt is the rate of change of magnetic flux with respect to time. So if the rate of change of magnetic flux with respect to time is more, the induced EMF in the closed conducting loop will be more. Similarly, if the rate of change of magnetic flux through the closed conducting loop is less, the EMF induced in the conducting loop will be less. Also notice the negative sign here. This negative sign has something to do with the Lenz's law, which we will explain and discuss in our next video. Here phi is the magnetic flux. As we know, magnetic flux stands for the number of magnetic field lines passing through a closed volume or closed surface area. Next, we will go through the Faraday's experiment to check how Faraday's law works. So, this is a small simulation tool which we will see to check the Faraday's law. So this is a magnet and this is a closed loop, and here the terminals of the loop are connected to a voltmeter and through a lamp. So if you just move this magnet toward the conducting loop, you can see there is a variation in the induced EMF, as you can see here in the voltmeter. Similarly, if you take this magnet out of the conducting loop, you see the induced EMF has opposite direction. I am again showing the experiment. Carefully observe. I am bringing this magnet into the coil. The induced EMF is in the negative side as this needle moves toward the negative side. Now I am bringing this magnet out of the coil. So the induced EMF has a direction toward the positive side. So as I discussed in the expression of induced EMF E equals to minus d phi by dt, there is something called negative sign. This negative sign has a meaning which I will explain in Lenz's law. I will also show you one thing. If you increase the rate of change of magnetic flux through the coil, the induced EMF will be more, as you can see. You check it. So from this experiment we can have some conclusions and some observations. So first of all, we will check the observation. As we have seen in our experiment, as the bar magnet is brought nearer to the loop, there is a deflection in the galvanometer. Here in the experiment we used voltmeter instead of galvanometer. If you have used galvanometer, the same response would have been there. This means that a current is flowing in the loop in a particular direction as shown by the deflection of the galvanometer. But the current can only flow if there is some EMF. This means there must have been some induced EMF due to movement of the bar magnet. I hope you understand this point. I will next go to our another observation. As the bar magnet is taken away from the loop, there is a deflection of galvanometer needle, but this time in opposite direction. What does this mean? This simply means that the direction of induced EMF has changed, and due to this change of direction of EMF, the current must flow in opposite direction. Next observation is that whenever we held the bar magnet stationary, there was no deflection in the voltmeter. So this means that if there is no change in the magnetic flux through the coil, then there will be no EMF induced. So now it's time to conclude. So in conclusion, we can say that Faraday's law, the induced EMF is dependent upon the rate of change of flux linking through the conducting loop or coil. As you have seen, when we have bowed the magnet fast toward the coil, the magnitude of EMF induced was more, and when we bowed the magnet slowly toward the coil, the magnitude of EMF was less. Therefore, to have an induced EMF, the flux through the coil must change. So this is one of the conclusion. It means the EMF in a closed coil can only be produced if there is a change of magnetic flux through the coil, which is evident because when we have kept the bar magnet stationary, there was no EMF induced as seen in the voltmeter. Next, as we know, flux is equal to dot product of magnetic flux density vector and area vector. This means that flux through a coil can be changed either by changing the magnetic flux density vector, or by changing the area vector, or by changing both. In electrical machine, Faraday's law of electromagnetic induction is most used. Therefore, I will suggest and recommend you to carefully understand this concept. Thank you.